So please go ahead.
I will not ask question. So today I will try to introduce the physics of silicon microresonator, and then I will try to give you a few examples. I should say that this slide have been prepared by people in my lab. So this is Stefano Biasi, Riccardo Franchi, and Boulan Aslan. And so yesterday we did a comparison between the semiconductor, the microelectronics industry and the photonics industry. And one point I made was the fact that in microelectronics you have a single dominant device that is the transistors, and this you know very well. So now the transistor is a three-terminal device with all the different input port. And in photonics, we do not have the same unified device, and therefore, so this is a large difference between the two technologies. So my point is that the microring resonator could play this role. And so what I'm trying to do today is to introduce you to this photonic device. And I will show you that as with the transistor, you have many free parameters in order to determine the properties of the transistors. Also, with this microring resonator, we have many different parameters that allow us to determine the most important properties of the microring resonator. Just to give you, and this is, you have to take notes, so these important properties, I will tell you why. Is called the quality factor Q, and is equal to lambda divided by the line width. And the other important quantity is the enhancement factor, that is the power that is stored inside the microring resonator versus the input power. Anyway, I will come back later on this. So let us start to introduce the physics of the microring resonator. So those are resonators, so meaning resonant devices. And they take inspiration by an effect that was observed at the end of the 18th century in several buildings. Here is an example in the St. Paul Cathedral. And this phenomenon is such that if you are, so this is the roof of the St. Paul Cathedral observed by below. And what happens is the fact that if you stay on the side of this circular room and you try to talk to a friend that is just on the other side, so on the opposite side, and you talk in this way, since the cathedral is very large, your friend do not understand anything. Okay, so the voice reaches your friend with a very, very low power, so he cannot hear you. But what is surprisingly happened is the fact that now, if you start to whisper and your voice is emitted along the edge of the cathedral, it happens that your voice, the acoustic wave, travel all over the border of the cathedral, all over the circumference, and reach without any attenuation your friend. And therefore, your friend can understand you. And this is the reason, and even your friend can understand you even though you are not speaking loudly. And so if you whisper with a very low volume, so your friend is still able to hear you. And this is the reason why these kind of modes that are confined by continuous reflection on the edge of the building are called whispery gallery modes. So they are modes that travel into a periphery of the building and reach your friend. In a very same way, people have used the very same physics, the very same concept, in order to describe what happens into a circular disk where you may have that an optical field is confined within the edge of the disk. And those are indeed the microresonator that we are dealing with. So they are nothing else than a looped photonic wire. So you take a photonic wire, so a waveguide, and then you make a circle by using this waveguide. And in this circle, you observe the very same phenomena that has been observed with acoustic wave in the St. Paul Cathedral. And this is the reason why they are called whispery gallery mode. And the looped waveguide is a micro resonator. Micro because the size of the disk is only, so the diameter of the ring here is only a few microns. And this is the reason why we call it micro resonators. So the micro resonator have a lot of application, and they are made by using the standard silicon photonics waveguide, meaning that you take 220 nanometer thick silicon, and then you shape this silicon waveguide either in a ring like this one, or you can shape into a racetrack resonator. So the name racetrack means because this looks like the racetrack where the horses are running. So the difference between the ring and the racetrack is that the ring is a pure circle, while the racetrack you have straight waveguide section here and there. Okay? Why do we have this straight section? Because we want to improve the coupling between what? Between the side waveguide. So what's happening? You see that here you have a waveguide that you place nearby the ring. And this waveguide here is called the bus waveguide because it is the waveguide that is used in order to input optical field inside the ring or to extract the optical field from the ring. And if you have only one waveguide, you call the system an all-pass filter. Okay? So we say that the geometry of the microresonator is an all-pass geometry when we have only one side waveguide. On the other hand, we may have two side waveguides. You see, here you have a waveguide, here you have another waveguide. You have the ring, and so in this case we call an add-drop filter. We will see in a while. Those are a few waveguides that we have fabricated. But then you can also play with the kind of structure that you can fabricate. Here is another example of those waveguides. You see that they are micro-resonator because you see the length scale here a few micron. And in this case, what you have is you have a waveguide on a plane, and then on top of this waveguide you have a disk. Okay? So you have, instead of having a lateral situation where you have the waveguide on the same plane as the ring, here you have that the waveguide and the disk are on two different planes. And these are configurations that are useful for optomechanics, but I have no time to talk about that. And even you can make a freestanding microring, like in this case, that is coupled to a waveguide. Okay? So those are all examples of the kind of structure that by using standard planar silicon technology you may get. Then you can also add on the microring resonator some other component. And therefore, instead of having a purely passive, only silicon there, you can make an active microresonator. Here is an example. So you have your microresonator here. You have the side waveguide that is coupling here. You have another waveguide that is coupled there. And then what you see here, so the white stripes are metallic lines. And those white stripes are used in order to make either a PN junction, like this in this case, or a thermal heaters. And so in this case, you can have a phase control here and there of the light that is traveling inside the microring resonator. Okay? And so that then you can change the properties of the microring resonator by injecting a current through these metal wires. And so this is the reason why they are called active microresonator. So now let us try to understand the physics of this system. The first very important point is the coupling between the microring resonator and the side or the bus waveguide. And so what you have here is the add-drop configuration where you have a bus waveguide, And so this is a standard waveguide where you insert your light. So the light is entering through this port here. So this is called a port. So it's entered into this port and is traveling in the waveguide. As you well know, when an optical field is confined in a waveguide, so you may also have that a part of this optical field is not traveling inside the waveguide, but is traveling on the side of the waveguide, okay? And so this field that is on the side of the waveguide may overlap with the field that is confined within the waveguide. And therefore, in this point here, we have a coupling. We have the possibility to have a passage of optical power from the bus waveguide into the microring resonator, okay? And this pass and the strength of the coupling is given by the overlap between the field that is confined within the waveguide and the field that is confined within the microring resonator. So that means that by controlling the distance between the waveguide and the microring resonator, you can control the strength of the coupling. The nearer is the bus waveguide to the microring resonator is, the stronger is the coupling between the bus waveguide and the microring resonator. So the kind of coupling that you can get here can be of 10%, can be of 30%, can be of 50%, meaning that 50% of the light field is coupled into the microring resonator. And now, if you get this coupling, what you can get is the fact that your light is coupled, okay? It's coming from the bus waveguide, is here. So this is an FDTD calculation of the optical field that is inserted into the bus waveguide. Then here you see that you have an overlap between the mode of the optical field and the mode of the microring resonator, and so you have a coupling between the two. And so you have that your field is passing into the microring resonator, and then is traveling in this whispering gallery mode of the microring resonator. And what happens is the fact that this field can be sustained by the microring resonator only in the case where you have a constructive interference between the field that is entered here and the field that is reaching this point after one round trip, okay? If you have destructive interference, it means that the field that is coming here is destroying the field that is trying to enter into the microring resonator. If you have constructive interference, you have that you are storing power inside the microring resonator. What is the condition for a constructive interference? So the condition is that the round trip phase should be a multiple of 2 pi. Okay? So you need to have that the phase of the light that is entering and the phase of the light that is reaching this point after a round trip, so the phase of the two light field should differ by a quantity that is an integer multiple of 2 pi. So then, if this is the condition, so you have that the condition for having a light field that is traveling inside the microring resonator, so the resonance condition is given by the fact that the optical length of the microring resonator should be a multiple of the wavelength, okay? And so this is the kind of resonance condition that should be satisfied in order to be able to insert power inside the microring resonator. So the resonance condition is that the effective index of the mode multiplied by the length, the physical length of which means the circumference of the microring resonator should be equal a multiple of wavelength. Okay? So this is one of the most important equation to describe the physics of the microring resonator. Yes?
I have a question here. So at the beginning, when I input the light to a side wave, for the first time, there will be no field inside the microring resonator, right? So there will be no constructive interference. It happens only once the wave travels entire circle and then it happens, correct?
Yeah, that's correct. That's correct. I will show you in a while, if you have time, that you can even compute the evolution of the field inside the microring resonator. Okay, here is the evolution of the field inside the microring resonator. But I will comment this in a while, okay?
Okay, thank you.
Other question?
Sir, when we come to this resonance condition, so that 100% light will be coupled or there will be some light passing through the throughput also?
Okay, so this is also another good question. So in this case, you see that the coupling is perfect. No light is going through. And this is called the critical coupling condition. I will tell more about. But if, for example, here the coupling is not as in this calculation, you have that also a small portion of the light is moving through. We will talk about that as well. But what is quite interesting here is the fact that you see that you are entering here, so the light is traveling there, and now when the light is reaching this other coupling point, so you may have also an overlap between the mode that is traveling inside the microring resonator and the mode that is traveling inside this waveguide. And therefore what happens? It happens that the light is entering here, is traveling there, and then a part of the light is coupled out in this other side. Okay? And so it happens that this kind of device, and this is the reason why it is called an add-drop geometry, by using this device you can add a light inside the microresonator, as well as you can drop the optical light from the microring resonator. And so you have that this can be used, for example, to channel your light signal from one port to another port. So you enter here, you couple, and you exit there. Okay? And so this is the reason why it's called an add-drop filter. And this you see immediately, you can notice here that when you satisfy this resonance condition, you have that the light is coupled to the microring resonator, start to circulate, and a fraction of the light is dropped, is exiting from this other port here. Okay? And so this is called, and this is the behavior of the microring resonator. So now if we do change the wavelength of the light, what happens is that we do have conditions, so wavelength, by which this resonance condition is satisfied, and therefore the light is trapped inside the microring resonator, or we may have condition by which this resonance condition is not satisfied. And for those wavelengths, so the light is not coupled to the microring resonator. So this means that now, if we do make a transmission spectrum, so we look the light that is coming out from this port as a function of the wavelength of the light, what we have is that we have, for those wavelengths there do not satisfy this resonance condition, we have that the light is not coupled to the microring resonator and therefore is passing through. And this is the reason why this port is called the through port. And so you have that the transmission here is equal to 1 because no light is trapped inside the microring resonator. Or we have other condition by which the wavelength satisfy the resonance condition, and in this case no light is going through, so the transmission is dropping down, while light is coupled to the microring resonator. In this case, so if the light is coupled to the microring resonator, you may have that some intensity of the light is coming out from this other port. And so now the red line here measure the intensity of the light that is coming out from this port. And what you see here is that when the resonance condition is not satisfied, you have that the light coming out from the through is equal to 1, and the light coming out from the drop is equal to 0. But now if you scan the wavelength, you enter the input waveguide by using a wavelength that is corresponding to a resonance condition. You have that in this case, the light from the the light from the through is going down, is dropping, no transmission, while the light from the drop is increasing, and you have a peak here. And so, depending on the resonance that you are considering, you have a series of dip or a series of peak in the spectrum of the light that is transmitted to the through port or is transmitted to the drop port. Yes. Yeah. So what you see here is the fact. So the question is quite good question. So it was saying why the transmission by the through plus the transmission from the drop is not equal to 1. Okay, yeah, this is also a good question. Okay, yes. So this is what I was saying you before. Yeah. So some light is still trapped inside the microring resonator. But at the same time, you have also that the waveguides are characterized by some losses. And therefore, you have that some light is lost. Okay? And so you have the sum of the light that is transmitted in the through plus the light that is transmitted in the drop plus the light that is stored in the microring resonator plus the light that is lost, and these four quantities should sum up to 1. Here you have some important quantities that you see that you have a wavelength separation between two nearby resonance. And this wavelength separation is called the free spectral range. Okay? The free spectral range is defined by the distance between two nearby resonances. Another quantity that is important is the full width at half maximum, that gives you how large is the peak at the resonance. Okay? So the largest is the peak at the resonance, the largest is the full width at maximum. And those two quantities are relevant for the calculation that we will do in a while. So now I hope that you have got the meaning of the microring resonator. So this is an add-drop filter. So typically we have an input port, a through port, and a drop port. So the resonance condition is given by the length, the physical length of the microring resonator, multiplied by the effective index of the silicon core waveguide. And this gives you the resonance condition. What you do observe here is the fact that the width of the peak depends on K, where K is nothing else than the factor that describes the coupling between the optical field in the bus waveguide with the microring resonator. So the larger is K, the larger is the coupling. And what you do observe here is that by increasing the coupling, you see that the line width, the full width of maximum, the resonance, get broader. Okay? The larger is K, the larger is the broadening of the waveguide. So, let us now try to be more quantitative. And so what I'm doing now, I'm writing down the equation that describe how the optical field inside the waveguide evolve with time. Okay? So this is a few mathematical equations. And so this is the equation that describes the temporal evolution of the field inside the microring resonator. And this kind of formalism is called the temporal mode theory. You should be able to understand what we are writing here, okay? So this is the alpha, is nothing else than the electrical field, so therefore is a complex quantity, is the electrical field inside the microring resonator. It's called the mode of the microring resonator. And so this equation tells you the rate of change of the mode inside the microring resonator. If on the other side here you have a negative contribution, it means that this contribution is going to decrease the intensity of the mode inside the microring resonator. If you have a positive contribution, the outcome is that the mode inside the microring resonator is going to increase. Okay? And so this equation tells you how fast, so the speed, the rate of temporal change of the mode intensity inside the microring resonator. And here you have several contributions. So the first one, so this is an imaginary contribution, tells you that this is the frequency, omega, the frequency at which a standing wave is evolving inside the microring resonator. And the reason why this is the frequency is because here you have I, the imaginary part. Okay? So it's the frequency at which the mode is traveling inside the microring resonator. Then you have a first negative contribution gamma, small gamma. And so this small gamma describes the losses that occurs while the field is moving inside the microring resonator. The larger are the losses, the faster is the decrease of the optical field inside the microring resonator. Then here you have a capital gamma. So capital gamma describes the coupling between the field in the bus waveguide and the mode that is traveling inside the microring resonator. And here you have a negative sign because if you are able to couple in light, the same light can be coupled out from the microring resonator. And therefore, if I'm describing how the mode inside the microring resonator is evolving with time, so this gamma factor should be considered as a loss because you are decreasing the power inside the microring resonator and you are transferring this power to the bus waveguide. And so here you have the frequency which with the mode is oscillating inside the microring resonator, the losses caused by the radiation out of the microring resonator of the optical mode, and the losses caused by the outcoupling of the optical field into the bus waveguide. Clearly, this equation is described a microring resonator geometry that is the all-pass geometry. And then here you have another term. And so this term here describes the fact that when you have an input light in the bus waveguide, so this input guide can be coupled into the microring resonator. And therefore, here you have a positive sign. And so this is the term that describes how much power from the bus waveguide is entering into the microring resonator. Now, what we want to compute is the transmission of the light by the bus waveguide. And therefore, what we do is that we do the ratio between the electrical field at the output of the waveguide versus the electrical field at the input of the waveguide. And so the ratio between those two quantities gives us the transmission intensity of the bus waveguide. And so if we do compute the ratio, so this is the ratio, this is the transmission, so you see that this transmission is equal to what you had at the input plus what you are coupling into the waveguide. Okay? And so this is given the transmission. Now we can isolate it for the transmission. We can solve in the stationary case, so by putting this equal to 0, stationary condition, we can solve this equation. And so we end up with a typical Lorentzian line shape for the transmission. And so this is a Lorentzian line shape where you see that the frequency is given by the difference between the resonance condition and the frequency of the input light, plus the width is given by all the losses mechanism. And so this is the kind of, where is it? And so this is the kind of result that we can achieve, okay? So let us assume that we have a condition by which we do lose as much light as we couple into the microring resonator, okay? So what we are doing is that in this solution, we are saying that the loss caused by the microring resonator are equal to the percentage of power, so the coupling coefficient, percentage of power that we use to insert light into the microring resonator. So we are equating, in this case, the power that we couple into the microring resonator by the power that the microring resonator is losing out of the ring resonance. In this case, so this coupling regime is called the critical one. And it is critical because at the resonance condition, at the frequency that satisfies the resonance condition, we have that the transmission is going to zero. Okay? So we are coupling a gamma factor of optical power from the bus waveguide to the microring resonator, and this power is completely lost. Okay? Because in this case you have that small gamma is equal to big gamma. Okay? You are coupling as much as you lose. And therefore the transmission is going to 1. Okay? And this is answering your question. So in this case, so we have that all the light that is coupled into the microring resonator is lost. Where it's going? It's radiated out of the microring resonator. It's small gamma. Small gamma. Light is radiated out. Why that? Maybe so you have some surface roughness. Why that? Maybe the radius is too small, and so that you have a huge quantity of light that is lost. Why that? Maybe you have absorption within the microring resonator. So you may have many different contributions that are sources of this small gamma here. While on the other hand, capital gamma is controlled by the distance between the microring resonator and the bus waveguide. Then you may have another condition where you have that, and this is called the undercoupling condition. You have that the coupling factor, capital gamma, is smaller than the loss, small gamma. So in this case, what happens is that you are inserting into the microring resonator less power that is lost by the microring resonator. And so in this case, since you are coupling a lower quantity of power, you have that at the resonance, the transmission is not equal to 0, because you still have some power that is going through the bus waveguide without being coupled and lost by the microring resonator. And then you have the other condition that is the overcoupling condition, where you are coupling more power to the microring resonator than what is lost. And also in this case, you have that the resonance is not going to 1, but is the depth of the resonance is not going to 1, but is slightly larger. Okay? Any question here?
Sir, we are taking y-axis as a mod of t square in place of directly t, and there is no drop filter here. This is like complete all-pass filter.
I missed the question.
So we are getting this as a resonance condition for critical one. So whatever light is being coupled, that is again coming out from the same filter, because it's all-pass filter, as you said. So there is no drop point here.
No. In this case, we do not have the drop.
Then also we will get this condition, the resonance condition.
Yeah, exactly. So if you add here another waveguide, you are in the add drop condition. And so the questions are very similar and the solution is similar. So in that case, what happens is that, let me stay here in the critical condition. So in this critical condition, you will have that all the power is dropped out. Okay? So the drop is going to 1. Okay? While in this condition here, in the critical condition, you have that the drop, in case of the add drop, you will have something like that. Okay, so then what is also important is the fact that not only the intensity is changed in the bus, in the transmission, but also the phase is changed, is affected by the kind of resonance condition that you are assuming. So in the case of the critical condition, you have no power out, so you cannot have a phase of the light out of the field. While in the case of the undercoupling condition, you have that the phase of the light that is coming out from the waveguide is equal to the phase of the light that was inserted in the waveguide. So you have a difference in the phase that is equal to 0. While in the overcoupling condition, in the overcoupling condition, you have that the difference in the phase is pi. Okay? Let us try to understand why we do have this difference. And so in order to understand why we have this phase difference, so what we have to do is that we have to do some math, meaning that in this case we have to actually solve the temporal evolution of the optical field. And in order to do that, so we use some math, so it's quite complicated math. But at the end, so you are able to compute. You are able to compute the time evolution of a square wave that is inserted into the microring resonator. And therefore, what you do is that you are let me see if I do have the... So what you do is that you are input into the microring resonator, you are input a square wave, meaning that the input field is 0 up to t equals 0, and then for a certain time, few nanoseconds, you have that the input field is large, and then you decrease again. Okay? So you are looking how this input field is transmitted as a function of time through the microring resonator. And this is the result. Okay? So what happens is the fact, so at time t equals 0, so you so you switch on the input field, and so you have some light is entering, is going through the bus waveguide, then a fraction of this light is coupled to the microring resonator and start to travel inside the microring resonator. And so now if you look at the intensity of the light that is coming out as a function of time, you have that the intensity of the light is starting to drop, and the reason why it's starting to drop is because you are starting to couple more and more light into the microring resonator. Okay? So this is what happens at the very initial instant of time. Then after the time for this one. So then after the time for a round trip, what happens is that now your field inside the microring resonator has reached the same point, which is the coupling point. And so in this case, what happens is the fact that now you have an interference between the input field and the field that was traveling inside the microring resonator. So in this case, for this calculation, so we are assuming that we are in an overcoupling condition, which means that we are coupling more light inside the microring resonator than the one that we are losing from the microring resonator. And therefore, what happens is the fact that here we have perfect destructive interference, because the light after a round trip has acquired a 2 pi shift with respect to the light that is entering. And so here, between this field here and that field there, you have perfect destructive interference. Within the microring, we have perfect constructive interference, but between the field that is traveling in the bus waveguide and the field that is traveling inside the microring resonator, you have perfect destructive interference. And therefore, the light intensity is going down to 0. But then you are still providing optical field, optical signal at the input. And therefore, what happens is that this condition of destructive interference now is occurring between a field that is large with a field that is small. And therefore, you have that the field inside the microring resonator is dominating with respect to the field is coming. And so you lose this condition of perfect destructive interference. And therefore, you have that a few of the field that is coming out from the microring resonator is transmitted by the bus waveguide. And so the intensity is increasing. And therefore, what you have is that at the initial time, you have some field that is transmitted. Then you reach, after a round trip, you reach the condition by which you get perfect destructive interference. And then, since you are providing more and more optical field inside the microring resonator, you have that the field inside the microring resonator is out coupled to the bus waveguide. And so you have an intensity that is transmitted by the bus waveguide. Are you following? And now the question is, what will be the phase difference between the field here and the field there? Do they have the same phase or do they have a difference in phase? Sorry? Why? Yeah, you more or less got the point, but the reason why, so the answer was correct. So between here and there, you have a phase difference. The phase difference is caused by the fact that the light that you get here is not the light that was entered, but is the light that was traveling inside the microring resonator and was exiting from the microring resonator. And therefore, while traveling within the microring resonator, it has accumulated phase. And therefore, you see this phase difference there. And this is the reason why you do observe this phase difference. And now, if you look carefully, you see that here you have a red spot, meaning that you are in a phase. So you have your wave. You have the positive part of the wave and the negative part of the wave. So the red one are the positive, let's say, and the blue one are the negative part. And so between the blue and the red, you have a pi phase difference. Okay? Wave, blue, red, pi phase difference. And indeed, if you look, here you have a blue, here you have a red. If you look, here you have a red, here you have a blue. So you have a pi phase difference. And the reason why you have a pi phase difference is because the light that is coming out here is indeed the light that was traveling inside the microring resonator. Okay? And then at the end of the pulse, when the input light is switched off, you still have some light that is coming out from the microring resonator. And the reason why you see this light is because it's the light that was traveling inside the microring resonator that is exiting. So this is the kind of physics that you do also here when you have a bell, and then you hit the bell, and you have the damping of the ringing of the bell. I don't have here an example to show you. You get the point. You take a bell, then you hit the bell, and you hear dong, 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 dong. And these dong, 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 dong are nothing else than the acoustic waves that are damping out, that are exiting from the bell, and the intensity of these acoustic waves are damping at the time. And this is indeed what you are observing here. So you have that the output intensity is going down, 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 down. And now I have a question for you. Why here I have a peak? So what I was saying is that at this time here, I'm stopping to input optical power in the bus waveguide. I'm stopping the input, so the input is going 0, but then in the output I have a peak with respect to what I had before. Why do I have a peak? Exactly. Exactly. So this is actually, indeed the correct answer, because in this here I do have interference between the light that is coming in and the light that is stored within the microring resonator. But they do have a pi phase difference, and therefore a pi difference in the phase, and therefore so the light here is negatively added to the light that is coming out from the microring resonator. When I switch off the input light, I no longer have this destructive interference, and therefore I have a peak in the transmission of the field. Now we can repeat the calculation for the resonant microring resonator when it is in a resonance, when it is in a critical resonance condition. And so if we do that, so this is what we do observe. And so we start with our light that is coupled into the microring resonator. So we have a peak of light. And then we do get, at a time after a round trip, we do get a perfect destructive interference between the light that is coupled inside the microring resonator and the light that is arriving from the bus waveguide. And this perfect destructive interference is preserved all over the time, and the reason is because in this case we have that the small gamma is equal to capital gamma. So the losses are completely balanced by the coupling of the light in the microring resonator. And therefore, at the end, so we still have the peak in the transmitted intensity at the end because of the removal of the input line. So now this plot here should be clear to you. And now let us see what happens in the case when we are in an under-coupling condition. So we are coupling less power than what is lost by the microring resonator. And so at the starting, so we have that the light is inserted, so our optical fields start to travel inside the microring resonator, and then after a round trip, we do get again interference between the light that is traveling inside the microring resonator and the light that is coming by the bus waveguide. However, in this condition, we have that this interference is between a strong field and a weak field. And therefore, in the transmission, what is prevailing is the strong field that is input. And so what you end up is the fact that now, if you look at the phase difference between the light that is going out from the bus waveguide and the light that is inserted, you see that the phase shift is equal to 0. So you have blue light here as well as blue light there. And the reason why you have blue light here and blue light there is the fact that this blue here is due to the light that is coupled in, and this blue here is due to the light that is transmitted through. Okay? And so in this case, so we have, by looking at the time-temporal evolution of the field inside the microring resonator, so we have explained the reason why in the undercoupling condition you have a zero phase difference between the field input and the field at the output, while in the overcoupled region, so you have that the field has suffered a phase shift of a pi between the input and the output. So those were calculations. So we also perform experiment, and here is indeed the experiment. So the blue line is the time evolution of the transmission of light through a microring resonator, and the red line are the result of the modeling that I've just shown you now. And so by doing this modeling of the experiment, you can also compute the value of the capital gamma and the small gamma. So you know the rate at which the coupling happens and the rate at which the losses happen in this microring resonator. So this is about the physics of the microring resonator. Here is a short overview of the kind of experimental setup that we are using in order to measure those microring resonator. And so just to give you an idea, so here is where the microring resonator are placed. So you see the microring resonator, the waveguide, so the coupling, in this case you have gratings to input and output the light from the coupling. So what you observe, since silicon is a semiconductor, so the properties are very sensitive to the temperature. So what we have is that we place our chip on a thermostat. So we have a Peltier cell there that control the temperature of and stabilize the temperature of the chip. And then here what you have is all the optics that is needed in order to control the input and the output optical signal from the microring resonator. So what we have a tunable laser Okay, so it's a laser by which you can change the wavelength. Then we have an optical isolator, which is used in order to prevent that back reflection enters into the laser and render the laser unstable. Then we have FS is everything is in fiber, so this is a cube beam splitter, but in fiber you need to have a fiber beam splitter. And so the input light is divided in two parts. So one part is going through this arm here, another part is going through this second arm there. Then we have an optical attenuator, variable VOA, a variable optical attenuator that is used in order to control the power that is indeed inserted into the microring resonator. Then we have some polarization controller to control the state of polarization, so to have either a vertical or horizontal polarization. Then we have another fiber splitter in order to monitor the power that is indeed inserted into the microring resonator. Then we have an optical circulator. You know, an optical circulator is a device that has 3 ports, and you have that the light from port 1 is transmitted to port 2, the light from port 2 is transmitted to port 3, and no light from port 2 is going to port 1, and the light from port 3 is transmitted to port 1. And therefore, what happens is that we have that now we have the input signal that is inserted into port 1, and it is transmitted to port 2. And so the light now is going this way, reach this port, arrive to this AS, what is AS? Alignment stage, arrive to this alignment stage, and then is inserted into the microring resonator. And then what happens is that you may have some reflection of light from the microring resonator, and therefore you have that the reflection of the light is coming out from here, and then reach the optical circulator in port 2. But this light is not going in this line, but is going here. And therefore, by using this photodiode here, so we can measure the light that is reflected by the microring resonator. At the same time, so the light that is transmitted by the microring resonator is reaching this other optical coupler and is going to port 3 and is measured by this photodiode. And therefore, by using this system, so we can decide whether to insert the light from this port or whether to insert the light from this other port. And we can measure at the same time the light that is reflected back or the light that is transmitted, or the light that is transmitted and the light that is reflected. And therefore, by using this kind of experimental setup, we have complete access to what is happening inside the microring resonator, and we can do a lot of interesting measurements. So this part here I'm avoiding because it's too complicated and I have no time. And what I want to show you is a kind of application of this microring resonator. So now you get the physics, and one application of the microring resonator is in the field of biosensing. And what we are exploiting here is the fact that the resonance frequency of the microring resonator depends on the effective refractive index of the optical mode. So this is the kind of signal that we are measuring in this application of our microring resonator. So the idea is the following. So we take a waveguide. And so we have that the field is confined within the waveguide. But when we say that the field is confined within the waveguide, we have to compute the shape of the field confined inside the waveguide. And what happens is that the part of this field, the evanescent tail of the optical mode confined inside the waveguide, is indeed traveling in the cladding of the waveguide. Now, if we have a waveguide that is air-cladded, it means that the evanescent tail of the field is traveling in the air. And now what we can do is that we can try to use this evanescent tail in order to probe what is happening on the surface of the waveguide. And therefore, so what we can do is that we can do a measurement of the refractive index when we have some liquid on the surface of the waveguide. But if we functionalize the surface of the waveguide in such a way that we put some chemicals, some biochemical agents, some molecules that are able to capture some analyte, so what we may have is the fact that these capturing molecules are able to capture the kind of analyte that we are interested to detect. And therefore, what happens is that those analytes are captured on the surface of the waveguide, and in this way they do change the refractive index on the surface layer of the waveguide. And therefore, what we are measuring as a function of time, we are measuring a change of the refractive index caused by the capturing of the analyte by the chemicals that were used to functionalize the surface of the waveguide. At the end, we remove the liquid, and we end up with some analyte that are bounded on the surface of the waveguide. As a result, what do we measure is the fact that the refractive index of the effective refractive index of the mode that is traveling inside the waveguide is changed. And by looking at the evanescent tail of the optical mode, what we can do is that we can probe whether those analyte have been captured or not on the surface of our waveguide. Okay? So this is the concept. Okay? So this is the concept that we are aiming to exploit in order to sense the presence of some kind of biomolecular. But what I have told you up to now is the fact that it's the refractive index that is changing. But in our case, what we have our resonance condition. And since the resonance condition depends on the refractive index, what do we observe in the transmission from a microring resonator where these analytes have been trapped? We do observe a shift in the resonance position. And so is this shift in the resonance condition that we are exploiting in order to make a biosensor. So the idea is very simple. So we have our microring resonator, whose surface has been functionalized by using some active molecular that is able to bind the kind of analyte that we want to detect. And then following the binding of this molecular, we do measure the shift in the resonance frequency. And by measuring the shift in the resonance frequency, we are able to quantify how many of those analytes have been bound. So this is the concept, and this is the kind of device that one has to build. So a device where you have the photonic circuit here, you have fibers that are used to couple the light in and out from the photonic circuit, you have the microring resonators that are functionalized by using the specific chemistry that you want to have, and then you have a fluidic system that is used to input the sample and output the fluid sample from the analyte. So one kind of application that we are using is this kind of concept is to look for contaminants in milks. The specific contaminant is a toxin that is called aflatoxin and is one of the major cause of contamination that can also kill people that drink contaminated milk. This is very severe here is in India, because if you do not screen the milk for the presence of this toxin, so then the people drink this milk and then get killed. Question?
Sir, last slide. Sir, where if we are getting any molecules of, suppose for biosensing applications, suppose we have cancer cell or something, so that wavelength shift which we are showing in resonance conditions, so that might be very less, which we cannot detect, or how much is the possibility that we can detect that shift in resonance?
I will show experiment on this. So the question is, are we able to link the specific shift with a specific biomolecular? Okay, so the question is not. What is make the difference is the kind of functionalization that you are doing. So the specificity is given by this binding here, not by this shift. The shift is only able to say whether you have something that has happened on the surface of the microring. But I will show you. And so this is the problem. And so this is the kind of chip that we have built where you see. So those are this resonator. So the system is quite complicated because you have to start from the milk. Then you have, the milk is a quite complicated liquid. You have a lot of fat, and so you have to remove the fat, so a lot of microfluidic. Then you have to concentrate in order to increase the signal. And finally, you have your detector here. The detector is our microring resonator. And the size of the microring resonator is few square centimeter. And here are a few data about the kind of rings that we are using. In order to get the high quality ring, so we use a very large microring resonator, so the radius is 100 micron. And then what we do is that we place more microring resonator in parallel in order to increase the amount of data that we are collecting. And this is the circuit that we are using. So here we have an input waveguide. Here we have a splitter, so a fraction of the power is sent to this arm here, a fraction is sent to there. Then here we have another splitter, and so 50% is going there, 50% is going there. Here we have another splitter, 50% is going there, 50% is going there. So at the end, so we enter from here, and we are able to send the same amount of signal on all those 4 different microring resonator, okay? So we do excite at the same time all the microring resonator, and therefore here we have 4 different output. Output 1, 2, 3, 4. And then what we can do is that we can functionalize differently the microring resonator in order to compare the results from the different output. For example, here we do not do anything. And so this microring resonator will be sensitive to the change in the temperature of the chip. Here we are not putting any specific capturing agent, meaning that everything that is coming can be attached on the surface. So this gives us the noise, the biochemical noise. While here we have the specific functionalization, and therefore here only if the toxin bind, so we see a change in the output signal. Okay? And so in this way we can really look at the influence of the environment, so the temperature change, or the influence of some contaminants, or the presence of the specific toxin that we are interested in. What do we expect as a function of time? We do expect the signal that is changing as a function of time. Here we do not expect from the output 4, so the signal in D, we do not expect any change in the transmission signal because we do not expect any change in the temperature caused by the flowing of the liquid. And therefore, so what we do expect is to have that the resonance shift as a function of time should be equal to 0. While here, in this case, no specific binding event, a very small signal, while here where we have specific binding events, so we do expect to have a very large signal. So this is the idea. So here is an example of the compact system that we have built. And here you see an optical image where you can notice all the microring resonator. Here you see the place where the fiber has been glued to the chip. the input. Here you see the place where the fiber has been glued as the output. Here you see the compact system. So this is the chip. Here is the PCB board where all the electronics that drives the laser, the photodetector, and analyze the signal are integrated. Here you have an input laser. So you send the light from the input laser through the fiber into the circuit. Here you have the photodetector, 4 photodetectors to detect the signal that are transmitted by the microring resonator. And this piece of plastic here is nothing else, the system that you use in order to handle the microfluidic, the liquid sample. Here you have the inlet flow, so where the input flow is going into the system. And here is where you have the output flow. And this is an example of the transmission as a function of time. So in this case, what you are doing is that you are putting some sugar, some glucose inside a water. And the more glucose you see, the larger is the refractive index difference. And therefore, you see that the shift is changing as a function of the amount of glucose, so as a function of the amount of the change in the refractive index. And so this is the resonance shift, and it looks like that the system is working. And indeed, if you properly functionalize the surface, you have that, depending on the quantity of toxin you have, you see that you have for, I cannot read here, for 12.5 nanomolar solution of toxin, you have a given resonance shift. If you double, you get more. If you have even more toxin, you get even more toxin. And the different lines are different cycle of measurements, so the measurements are very reproducible. And here you see what happens when you look for a non-specific binding. So this is answering to your question. So you have functionalized the surface in order to be able to capture this toxin that is called aflatoxin M1. And so this is the kind of analyte the kind of toxin that you want to detect. And so you specify your chemistry in order to capture only that one. And indeed, when you use another kind of toxin, so this is ochratoxin, the one that is not captured by your functionalization, you see that the resonance shift is essentially negligible. Okay? And so this means that you have a very specific binding of the analyte, the toxin that you want to detect, to the surface of your microring resonator. And so this is one example of the application of the microring resonator. And at the end, so this is the kind of system that we are using. And this system is quite large, it's quite big. And the reason why it's so large, it's so big, is because we have to treat the milk, not the sensor. So the sensor is extremely small. And everything can be packed inside a box. And this is a box. So this dimension here can be half a meter. It's quite heavy because of the pump, because of all the pumps that you need in order to handle the different sample in the system. And the actual biosensor is extremely small. Should be somewhere here. Okay, all the rest is because of the liquid handling. Okay, here is an example. Now I want to show you and discuss with you another example of the use of this microring resonator. And the example is the use of this microring resonator in a nonlinear regime, where they do show a situation that is similar to a chaotic system. And so in this case, what we are interested in is to look at the temporal response of the microring resonator. Okay, so in this case, what you have is a microring resonator in the add-drop configuration. Just to give you numbers here, so so this is the typical silicon nanowires. So here is the silicon oxide top cladding, 750 nanometer, and the diameter of the microring resonator in this case, so the radius is 7 micron. Okay, yes? That's a good question. So we do have developed a process in order to reactivate the sensor. However, for application, they do not want to use an already used sensor. And so from the point of view of the real application, so you never reuse the sensor. So use the sensor only once. Every time you have to replace the sensor, yes. And this is what makes the business interesting, because you can sell a lot of sensor. Can you imagine that I do use a 300 millimeter wafer to make those sensors? So those sensors are extremely small, 1 centimeter square. So by one single run, I can make, 10,000 of those sensors, okay? And then I'm selling those 10,000 sensors to different farmers. And those farmers use the sensor for several testing, okay? And so my business is essentially negligible because I'm selling only a few of those sensors. Instead, if each time they do testing, so they have to replace the sensor, so I have a large market, and therefore I can process many wafers. Yeah, the reason why the farmers were interested is the fact that instead of using our sensor that show a response in a few minutes, you see here, you take 5 minutes in order to get a stable output, meaning that in 10 minutes you can make a testing of your, if you use standard chemical methods, so PCR or whatever, you have to take your sample, send the sample to a chemistry lab, and then waiting for the reply from the chemistry lab, and that takes days, okay? And this is the reason why they could be interested to this kind of application. And indeed, so the main problem here, so this was an activity that we performed, I think, 10 years ago. You see, this is the USB connector, is a micro USB. So the micro USB were used maybe 10 years ago, okay? And so what is unpractical in this configuration is the fact that you see that you do not have the possibility to remove in this packaging, the possibility to remove the chip, okay? And now, so there is a company in Trento that are using this kind of sensor, and the idea for them is to use a cartridge by which everything is fixed. So they have a small system where they have the laser, the photodetector, the pump, and the microfluidics. And then they have a cartridge that is the photonic chip that they do insert, they do the analysis, and then the photonic chip is disposable. And their business is selling clearly the system, but also the cartridge. Okay. But I wanted to tell you about some kind of other applications. So here we have the microring resonator, and this is the spectral response of the microring resonator. Okay, the radius was 7 micron. Okay, so you have a peak, so several peaks because of the different resonances. But now if we look at the actual measure, temporal response of the microring resonator, so if you are in a situation where you are coupled with a microring resonator, you see a constant signal. Some noise, because these are instrumental noise, but the signal is constant. And now you start to increase the input power. And if you start to increase the input power, you are moving from a linear response like this one, to a nonlinear response where the properties of the microring resonator depends on the input power. So the basic physics here is associated to what is happening into a waveguide when you increase the optical power of the light that is traveling through. The wavelength of the light that we are using is a wavelength where silicon is transparent, 50-50. Okay, so we are in the C band. So silicon here is transparent. However, if you increase the optical power at the input, you are entering in a nonlinear regime where other effects start to play a role. In this case, what is happening is the fact that you are entering in a regime where two-photon absorption is important. Any one of you knows about two-photon absorption? Ever heard about two-photon absorption? So this is an effect by which we are going into, so it's an effect associated with Chi3. You know anything about Chi3? You know the polarization? The polarization vector, okay? And so you know that the polarization vector typically is equal to the electrical susceptibility times the electric field. And this is the linear response. But then if you start to increase the optical power, you see that instead of having a linear relationship between the polarization and the electric field, so this is the linear relationship between the polarization and the electric field, you enter in a regime where this relationship is no longer linear, okay? So if the power of the field, so the intensity of the electric field is increasing, so you are departing from a linear relationship and you end up with a nonlinear relationship. So you can then describe those nonlinear effects by adding here terms. Okay, so this is, you say, is Q1. Here is a term that is K2, and then here you have other terms. Okay, so a term that is proportional to the square of the field, Chi2, a term that is proportional to the cube of the field, Chi3. Okay? This is the second, is named second order nonlinearity. And the second order nonlinearity is the reason why, for example, you have second harmonic generation. Second harmonic generation. The third order nonlinearity, you may have third harmonic generation. And all effects like that one. And this is third order. And so those are a nonlinear response of the material. Among the third order nonlinearity, there are effects like third harmonic generation. There are effects like two-photon absorption. There are effects like four-wave mixing. There are effects like Raman scattering. Those nonlinear optical effects are all very important. Silicon is a centrosymmetric material, and therefore silicon has no second order nonlinearity. Silicon has only third order nonlinearities. And this is something that is very important for the application that we will talk about, these third order nonlinearities. And there are two main third order nonlinearities that we are using. The first one is called two-photon absorption, TPA, two-photon absorption. The other one that we are using, that we will use, is called four-wave mixing, and is four-wave mixing. And this is we will use this one when we will talk about quantum physics, because it's the kind of nonlinearity that we will use in order to generate entangled photon pair. So, two-photon absorption is a process by which you have two energy levels, E1 and E2, and you want to move one electrons from level E1 to level E2. Okay? So typically, in order to do that, so since you have to conserve the energy, you need to have that the energy of the photon should satisfy the energy conservation rules. So the energy of the photon should be equal to the energy difference between the two levels. Okay? And therefore now, and this is absorption, standard linear absorption. But now, if the photon energy is smaller than the band gap of the semiconductor, so we cannot absorb that photon, okay? So the semiconductor is transparent. However, if the optical power is large enough, in order to enter in a region where we have a nonlinear response of the material, it may happen that two photons are absorbed at the same time. And those two photons, the energy of those two photons adds up in order to satisfy the condition by which the energy difference between the two levels is now equal to 2 times the energy of our photons. Okay? This process is called two-photon absorption. Okay? So typically, this photon is transmitted, is not absorbed, but if the intensity of the beam is large enough, we may have that two photons adds up in order to overcome the energy difference between level E1 and level E2. Okay? And so this is a process by which we do absorb, if we do absorb light by absorbing at the same time two photons. And the process is called two-photon absorption. As a result of this two-photon absorption process, we generated free carriers. And so we have our silicon. We have our silicon, so this is the band gap of silicon. The band diagram of silicon, energy versus momentum. So this is the valence band. This is the conduction band of silicon, so this is the conduction. And what happens is that we are entering with a photon in the third telecom window, so 1.55 micron. And this photon is typically is not absorbed by silicon, because silicon is transparent. But if now we have here many of those photons, a few of them can be absorbed by two-photon absorption. And therefore, as a result, what we end up is that we do generate free carriers, so free holes, and free electrons. And so we generate free carriers by two-photon absorption. Okay? Clearly, this process is a nonlinear process, meaning that the more power the input light has, the larger is the generation of the two photons, of the free carriers. Okay? The lower the power, the less is the generation of the free carrier. The lower is the generation of the free carrier. And therefore, at the end, so we may end up with no photons, no free carriers generated if the optical power is too small, or a large amount of photons of free carriers that are generated if the input power is large enough. Yesterday, I showed you that if we have free carriers, we can use free carrier to modulate to change the refractive index, the Sorev relationship. And therefore, it happens that if we do generated free carriers, so we have a change in the refractive index. And so that, what does it mean? It means that now the refractive index is depending on the input optical power. Okay? The larger is the input optical power, the more two-photon absorption events happens, the more free carriers we have, and those free carriers, through this relationship, change the refractive index. And therefore, we have that the refractive index now depends on the input optical power. We have a nonlinear effects, a nonlinear dependence of the refractive index on the input optical power. And this is what is schematically shown here. So you have the valence band, the conduction band, and then you have your input photon. And a few of them can induce, by two-photon absorption, the generation of free carriers in the conduction band, free electrons in the conduction band, and free holes in the valence band. And this is the effect of the free carriers. But then those electrons and those holes do thermalize, meaning that they do lose the extra energy. And in the thermalization process, it happens that they do emit phonons. And so we have a multi-phonons generation inside the semiconductor. But the phonons are lattice vibrations, so the lattice starts to vibrate, meaning that the temperature of the lattice is increasing. And therefore, following the thermalization of those free carriers, we have that the semiconductor heats up. I have already said that if I do increase the temperature in the semiconductor, I do also change the refractive index. And therefore, in this case, we have two different phenomena. So the first one is the thermo-optic effect that causes an increase in the refractive index. And the reason why the refractive index changes because the free carriers here thermalize. And so we have an increase in the refractive index. But at the same time, the free carriers do affect the refractive index. And therefore, we have also a free carrier. It's called a free carrier dispersion, meaning that we have a change of the refractive index caused by the free carriers. What is quite interesting for the application I'm going to discuss is the fact that those two effects have a different sign. So in one case, we have that the increase of the temperature, or the change of the temperature, cause an increase in the refractive index. On the other case, we have that the increase of the free carrier concentration cause a decrease in the refractive index. So they increase in one case, they decrease in the other case. And therefore, the dependence of the refractive index on the input power depends on the increase or decrease of the temperature and of the increase and decrease of the free carrier concentration with a different sign. Okay? What is also very important is the fact that the typical times at which this effect happens are different. So the typical times for dissipating the heat developed by this thermalization process happens on a time scale of 100 nanoseconds. So this is the time scale of the temperature change in the microring resonator. And the typical times of recombination of the free carrier is 4 nanoseconds. So this is the time that takes the free carriers to thermalize, to disappear. And this is something that we will see. It's playing a crucial role in explaining what I'm going to tell you in a while. So then, since we have a difference, a power dependence on the refractive index, we have also that the resonance of the microring resonator change. Okay? And the change is quite interesting because we may have a change towards the blue. So a blue shift in the resonance caused by the increase in the free carrier concentration, or we may have a change in the red caused by the increase in the temperature. So we have two effects that are pushing and pulling our resonance. One is pushing the resonance to the blue. This is the free carrier dispersion. And the other one is pulling the resonance to the red, and this is the thermo-optic effect. So we have something that is pushing and pulling the resonance on one side or on the other side. So as a result, it happens that the resonance starts to pulse. So we have a pulsing, a dynamically continuous movement of the resonance because of the effect of the free carrier dispersion that is pushing the resonance to the blue and the effect of the temperature change that is pushing the resonance to the red. Okay? So this is the result of the balance between those two effects, free carriers and the change in the temperature. But now, if we look at the light that is transmitted at a fixed wavelength, you see that the transmission of the light now is no longer constant as a function of time. So you see that the light that is transmitted starts to increase, and then is going down. It is increasing, then passing the maximum, is going down. So that happens in the microring resonator is the fact that now, depending on the input power, we have a CW input power, a constant input power, and then the transmission in the drop in this case is pulsing, okay? Because of those two effects. And so we have an effect that is called a self-pulsing effect. So the microring resonator transmission starts to pulse even though the microring resonator has been input by a constant beam. And this is something that you can simulate or even experimentally observe. Just to give you a few numbers, so the microring in this case had a radius of 7 micron, and the gap, so the distance between the bus waveguide and the microring were of 180 nanometer, was 180 nanometer. So this is nice, okay? And this is what is happening. We will see an application of this phenomena later. But this is what is happening when you have a single microring, okay? A quite periodic self-pulsing. But now the question is, what does it happen if we put, instead of a single microring, so we put many microring in a sequence? So this sequence is called a side-coupled integrated space sequence of resonator, or in short, scissor. So in this case, what we have one microring resonator, another microring resonator, another microring resonator, and then the spacing between those microring resonator is fixed. Okay? Give you numbers, so the radius here is 7 micron, and the spacing can be 10 micron. Okay? And now we put this microring resonator into a self-pulsing regime. So the situation is very similar to the situation of a series of pendula that are coupled together, okay? And here the physics start to get interesting, because in this case, what we do enter into is a situation quite complicated. Why is quite complicated? Because we have that this pendulum here start to oscillating, but due to the fact that you have this kind of sequence, this pendulum is also coupled to the nearby pendulum. And so also this pendulum here start to oscillating, okay? And from the optical point of view, so what happens is the fact that now you are input a light, a CW light here. So this light is coupled to, let's say, this microring resonator. Some light is dropped to this other microring resonator. And so this microring resonator is transmitted a part of light that is recoupled to this microring resonator, that is transmitting some light that is coupled to this microring resonator, and then some light is dropped by this microring resonator that is coupled to this other microring resonator. And therefore here you have a situation by which all the different microring resonators are coupled together. It's exactly the situation of a pendulum, where each one of those, of a sequence of pendulum, where each one of these pendulum is coupled to the nearby pendulum by a spring. And so it's a quite messy situation, it's quite complicated situation. And so what happens is the following, okay? So this is the transmission of the light as a function of time in this scissor case here. And what you do see here is the fact that if you are using a given wavelength and a given power at the input, you may end up in a situation where you are coupling together only two of these microring resonators, and therefore the transmission is a very well periodic signal. By the way, those are not, these are not calculations, so these are experiments. And so what we were doing here was to have our microring resonator and then taking an image of the light coupled to the microring resonator by using an infrared camera. Okay? So you have that the light is going through the microring resonator, a part of this light is scattered out of the microring resonator, and what we are measuring here is indeed the intensity of the light that is scattered from the microring resonator. So if you are able to couple light into the microring resonator, you observe a very well localized scattered image of the light. For example, here you do not observe any light coming out from this microring resonator, while here you do observe a lot of light. Why do we see this difference? This difference we do see because when we do fabricate the microring resonator, so they are all nominally fabricated with the same, parameters. Let's say, for example, that we are fabricating our microring resonator in a fab, and we say that we want that the radius is equal to 7 micron. Okay? And so this is what we designed, 7 micron. But then the fab is processing with a lithography process which has a resolution of 5 nanometer. And so this is the resolution of the fab. So that means that the radius is not 7 micron, but is 7 micron plus or minus 0.005 micron. Okay? And so one can say, okay, come on, this is negligible with respect to the 7 micron, isn't it? Huh? So it's very small, so it's 1,000. But then you look at the wavelength, the resonance wavelength. So lambda is equal to 2 pi n times r. And then here you have m. Okay? So then now, so we are measuring the resonance position. And so the resonance position is 1.555 micron. Okay? But then we are doing measurements with a laser that has a resolution of a picometer, of 10 nanometer, of 1 nanometer. And therefore, so we are really sensitive to the single position. And this is indeed what is happening here. Okay? So what is happening here is the fact that we have two rings that have nominally the same parameter, geometrical parameter, but they have a different resonance because of the lithography resolution. And so this ring can have a position of 1,555.3 nanometer, and this is the peak at this wavelength. But this one has 15558 nanometer. Okay? So very tiny difference. But from a spectral point of view, so we are very sensitive to those differences. And so they have resonances that happens at a slightly different wavelength. And this is what you do observe. So this is the wavelength, and this is the transmission spectrum. And you see that in the transmission spectrum, each one of these rings, even though they are nominally equal, because of this lithography resolution, they have a different resonances. And therefore, so when we are entering with the wavelength, so we are not with this wavelength, so we are only excited those two rings. And those two rings start to self-pulse in a very coupled situation, in a very periodic situation. But then, what do? We change the wavelength, and now we are exciting other three rings. And in this situation, we have three rings that start to oscillate together. And those three rings that start to oscillate together show a pattern that is completely different with respect to the clean and periodic pattern, and start to be aperiodic. But then we change rings. And in this case, we have a very, very complicated pattern. And this pattern is a chaotic pattern. Okay? So what we are observing is a chaotic evolution of the transmission of the light through these micro rings. So we are moving from a periodic self-pulsing to a chaotic one. How can we be sure that this is indeed chaotic? You know that chaos is very sensitive to initial condition. So this is the butterfly paradox. You know the butterfly paradox. People are saying that a butterfly in Brazil can influence a storm in Europe. And the reason is because of the strong influence to initial condition of any system. Okay? And so in the case of a periodic system should not be sensitive to the initial condition. A chaotic system is strongly dependent on the initial condition. So even a small change in the initial condition will affect a very different evolution of your system. And here is an example of what is happening in the case of a periodic case where we are not at all sensitive to the initial condition. So the periodic case is this one. Okay, so this is the periodic case. And what we do in order to change the periodic condition was a very simple experiment. So we have our CW laser that is exciting, is pumping the system, and we put a hand and we remove the hand. So we reset the initial condition. And so the initial conditions are slightly different because when we stop the input power, so the laser can have a difference in phase or whatever. Okay, a small difference, simply a small fluctuation in the power intensity. And so we are changing the initial condition. And in the case of a periodic situation, we have that the response after a given time, before and after, is exactly equal. So you see that the green and the red traces overlap perfectly. The situation is different when we are in a chaotic cases. In a chaotic case, what you see after a while, that the system starts to be stationary, so you see that the two evolutions are completely different. So this is the green line and this is the red line. So they are very different. And so indeed, we are really into a situation where we have a chaos. What can we do with chaos? We can generate random numbers. Okay? And so in this case, you have a system where you can use in order to generate a random optical bit pattern. Okay? And so in this case, so the kind of device that we have built was a sequence of parallel scissors, and then with a single output. And what you do observe here is the fact that now you have a quite chaotic generation of random numbers with a very good randomness. at a frequency of a few megahertz, so meaning 50 millions of random bits are generated by exploiting this chaos. And you have that those bits are directly generated in the optical domain. Okay? So this is a sort of system that exploits the self-pulsing, so the nonlinear properties in our microring resonator for a cryptographic application. Any question? So if you do not have questions, so here I have a list of papers. You will see those papers in the slide notes, so you will receive the slides. And those papers are a few papers that we have published along the year on this topic, and where all the description I gave are detailed also from a formal point of view. So all the mathematics is there. Okay? So if you do not have any questions, so I finish here. Maybe we can have a coffee or a tea break. Okay, so then we can move. I turn off.
Again, start at 12 o'clock?
Yes.
Half an hour break?
Sì, sì, it's okay.
Only how much break do you require? Depending on you, we can start. Like when do you want to go for lunch?
How was the program now?
No, so the next is at 12 to 1.
Yeah, that's good.
So we just ended.
So the end was at 10, so it was longer than. You had to make me.
So we can start at 12 and 12 to